Welcome to our third lecture in operating systems engineering. So today we're going to take a closer look at how, when we start with a simple program that's executed on a computer and which uses maybe library functions, how we can get from this to actually use an operating system. So we're going to talk about history of operating systems for a bit, and then we'll dig deeper into how function calls and how requesting functionality from an operating system works on RISC V. So today we're going to take a look at tasks of an operating system, then initially the operating system as a library of common functions. Then we are taking a closer look at how RISC V is handling or supporting operating systems. So there's so-called privilege modes that are supported in hardware by a CPU, which make it easy to distinguish between code running inside of the operating system, which has privileges, so can access the hardware, for example, and code running in your user mode processes, which is not allowed to access hardware directly. Then we take a look at the specific mechanisms of RISC V, how to configure this using so-called configuration and status registers, how to switch between the privilege modes. We do this using something called system calls, which are the mechanism to request functionality from an OS. And then we need to take a short detour to what we call physical memory protection. So these privilege modes also incur some more protection against unwanted or malicious access to memory. And then finally, we take a look at how we can implement and how we can call a system call. So we're taking a look at the operating system side that implements the system call functionality, as well as the user mode side, which actually has to have a way to call your functionality in the operating system. All right. So why on earth do we actually want to have an operating system? Now, back in the days when computers were new, they were very expensive. So having a personal computer or a couple of computers for yourself was absolutely impossible. So if you bought one very expensive computer, you somehow had to share this computer among multiple users, and so each user wanted to run at least one different program. So you had to share your computer among different multiple programs. And the idea was that programming the hardware directly for an end user like a physicist who wants to run a simulation of a neutron star, this user / programmer doesn't really want to be concerned with how do I output stuff on the printer, how do I put bits on the screen, how do I read something from disk. This user wants some more high-level abstractions. So the idea of an operating system was to provide a more useful set of services on a higher level than what the hardware provides. So we want to manage and also abstract the low-level hardware of our computer. And one example here is that a word processor does not actually need to know which type of hard disk is in your computer, because it expects all hard disks to look the same, or it doesn't even care about if it's a hard disk or an SSD or a RAM disk, or maybe even just some file system mounted from the other side of the planet. So this is on a completely different level, and the operating system has to serve as the connecting piece to connect these high-level abstractions with what is available on the low level, like a disk controller or a network controller for remote access. So the idea was to share this expensive hardware among multiple programs so they can run or appear to run if you only have one CPU at the same time. And of course, with modern computers, we still need this, even if you're the single user. You want to run something in the background. So when you're browsing the web in the front, you maybe want to listen to an MP3 file in the background. Your master thesis is being spell checked, and whatever is going on in the background, Bitcoin mining or something like that, you know. So when we share a computer among multiple programs, what can happen? Well, essentially, if all goes well, we wouldn't need any protection. But programs have bugs, so a program can inadvertently read data from another process that might not be so critical, but it can also inadvertently overwrite memory of another process. Obviously, this is critical just because then this other process would probably produce incorrect results. In addition to these accidents, there's of course also malicious software nowadays. So malware like viruses, Trojan horses, stuff like that, which try to, for example, extract your credit card numbers from your web browser where you do your online banking, or run a Bitcoin miner in the background which you don't want to run, stuff like that. So essentially, we need a way to provide controlled interaction between different processes. We need a way to constrain what a process can do. We need to enable processes to share data if it's required. We need to enable them to work together, but by doing all this, we need to set limits to ensure that consistency, privacy of the data of each single process is guaranteed. So how were the first operating systems developed? So the early computers in the 1950s were not just expensive and mostly just built in very small numbers, but they were also single program machines. So they were very primitive. Essentially, you would load a program into the computer from external media, which back then was like a punched card or paper stripe or something like that. Then the operator of the computer, so you were not allowed as a user to touch the computer itself, the operator would then execute that program. Then the result of the program was usually some printout on paper. So after a printout was generated, well, which sometimes just said error or sometimes gave the correct results depending on if your program worked or not, then this program was just purged from the computer's memory, and the operator would just load the next program in queue. So you had to hand in so-called jobs, which consisted, for example, of a large number of these paper punch cards, which contained whatever your executable programs, and there was no sort of interactivity. Sometimes you had to wait, especially as a student, for a day or more for your results to appear. Now imagine if you had to hand in your exercises and you had to hand in your program a day before, and it took a day of turnaround time to know if your program actually compiled and generated the right output. So we have it a bit better nowadays. In addition, when you have this single program semantics, so you load a program, execute it, and throw it away out of the computer, then essentially all programs had to re-implement certain functionality. And this functionality is what we nowadays assume as a given OS functionality, so access to disks or printers. And this was tedious, this was error-prone. So the first thing that was developed already in the 1950s were just function libraries of reusable common functions. So there was a single function developed by somebody that was able to print a page of text on a printer or to access something on the disk. And these libraries were reusable, so every user could link them to his or her own program. And then, of course, some people had the idea of, well, loading these libraries, because they grew pretty large for the time, loading these libraries takes quite some time. Why can't we just leave this library in the computer, so in the computer's memory, all the time? Because like 95% of our programs are using them anyways. And of course, if you do this, you need to protect this library somehow so that one of the user programs doesn't inadvertently just kick out the library or modify it or whatever. So this was the idea to implement protection and also privilege modes, because then our user programs should no longer access the hardware directly, because that was the task of a library. And so a privilege mode was then introduced as a hack, of course, first, to restrict access to the library's memory, to restrict access to the hardware directly, so regular programs couldn't mess around with our computer, with our data, except for the data and code they were using themselves. So if we talk about function calls, well, that's obviously the way a library works. We need to take a closer look at how these work on the machine level. So on RISC V, we see these two functions here. So on the left-hand side, you just see two very simple C functions. On the top, there's a function called add, which takes two integers and returns an integer, which surprisingly should contain the sum of the two parameters which we pass. And then on the bottom we have another function called foo. This doesn't take parameters, so it's void. It returns an integer and just returns this result of a function call, and the function we call is exactly our add function, and we give it 2 parameters here. So this C code looks simple, but remember, assembler doesn't have any notion of structure. So assembler is really going on the bare machine level. So it just knows about addresses, but it doesn't know about functions and function names. Assembler also doesn't know about variable names, so it doesn't have an A or a B. It just has memory locations again, or CPU registers. So CPU registers are just very, very fast, but very small storage locations inside of the CPU, and these are used to hold intermediate results. And for RISC CPUs, like our RISC V, but also an ARM processor in your smartphone, most of the arithmetic and logical operations, like adding something or doing an XOR, has to be done on the register values. So you cannot execute these directly on memory locations. You first have to load a value from memory, then you have to operate on it, and if you need the result later, you need to store it back to memory so you can use it later. So our function foo looks like the one on the right-hand bottom side. So essentially, we load 2 registers, A0 and A1, with an instruction which is called li. Li just means load immediate. So we just load a constant into a register. And we see to call this add function inside of foo, we need 2 parameters, 23 and 42. So we load 23 and 42 inside of these registers A1 and A0 respectively. And then we somehow need to call our function. So we do this by using this JALR function, jump and link register, which is shown in red here. So a jump means we change our program execution, our program flow, so it's no longer linear, but it switches to somewhere else. And this is essentially an address which is calculated as 0100 here. Now, compared to a regular jump instruction, which would just jump, the JALR function does something in addition. The JALR function remembers where it came from. So there's a special register inside of the CPU called the link register, LR, which is used to store the return address. So what we want is a function call. So we want our program to continue executing after this function we called with JLR has finished executing. So what we do with JLR, or the CPU does this for us, it stores the address of the instruction following the JLR, so our JR instruction here, inside of that link register. So we can actually use this to return to the function. So we use this call to a function and we jump to address 100, which is our add function on the top right. And this just has one instruction, so it adds a word, so a machine word is 32-bit, for example, and it adds the 2 parameters on the right-hand side, so the contents of registers A0 and A1, and stores the result again in register A0, because we don't need that value anymore. And now we need to return from this add function, and we do this by calling a jump instruction. JR is jump to register, and you see here the link register is missing, so we just jump to the address which was stored in a register, and this register is now exactly this RA we were using. So we stored our return address, so the address of the very last instruction shown on our slide here, the JR instruction in foo. We stored it automatically in our RA register when calling JLR. Our function add does its functionality, it adds 2 numbers, and then it jumps back to the stored address in RA, and we end up at our last instruction here, which again jumps back to the contents of RA. That looks good, does it? Let's see. Now 2 things we need to mention here is how do we know in which registers we actually pass parameters? Now there are standards for this. They're called the ABI, the Application Binary Interface. So for RISC V, for example, it says that the first parameter to a function should be contained in register A0, the second one in A1, and the return value of a function should again be passed in register A0. And we see this here. In foo, we load our first two parameters, 23 and 42, into these registers A0, A1, and our function add produces the result of the addition in register A0 again, which is our designated return value register, and then jumps back. So we need to note that this is just a convention. If you want to use other registers, you could do this by changing your compiler backend. But then your code won't ever be able to interact with existing library code which uses these common conventions. So this is just a convention. There's nothing in hardware enforcing this. This is just a compiler generating code when you call a function that passes parameters in A0, A1, and so on, and expects a return value back in A0 when you return from a function. If you want to use other registers, you could, but obviously it's not recommended because then you'd have to build all your libraries yourself. Now, does it really work? Wait. There's a problem. So in programming languages, you have something called a scope. So if you define a global variable x, for example, and inside of your own function you declare another variable x, then this variable x, which is defined in the most inner scope, so in your function, this would actually what we call shadow the other variable. So the global variable x would no longer be visible inside of that function, and you'd have a separate storage location for your local variable x inside of your function. Now this is not how a CPU works. So inside of the CPU, each register, even if it stores variable values temporarily, each register is only available once. With some exceptions for some CPUs, but for RISC V, it's exactly that case. So you only have one A0 register, and if you load a different value into A0, well, the old value is overwritten and lost if you don't store it. Now RA is just a completely regular register. You could actually use a different register. So using RA on RISC V is also just a convention. And if we take a closer look, then we see in this line marked in red with our JALR instruction, we override RA because we need to know where to return to, which works fine because in our green instruction and the add function, we read RA and jump back to it. Now, when we jump back to it, we jump to our pink instruction on the bottom. And that's where our problem starts, because each function assumes that it can just return to a return address, which was stored when the function was called. But if we call another function, either ourselves recursively, or in this example, our add function from inside of foo, this RA register will be overwritten. And as I just said, a value that's overwritten, well, it's gone. So where would we jump to here in this case, JRA? Well, RA was just overwritten by the previous instruction, by the JLR, with the exact address of this JR instruction, because that's where JLR wants to continue our code after our add function returns. So this means we would build an endless loop because RA, in our last instruction here in pink, was overwritten with the exact address of this JR instruction. So this is no longer correct. And here we have a problem. And we need to solve this, obviously, because otherwise we could just call one level of functions. You could not do recursions. You could not call a function from another function. And that would obviously be a bit constraining. Now we need to add something here. If you look at the footnote, there is actually no JRA instruction. It's just a pseudo instruction. So all jump instructions are actually jump and link register instructions. So they always store the return address. Now, if you don't need this return address, there's a special register in RISC V called X0, which always contains a 0. So you can write anything in it, but when you read it again, it's a 0. So it's essentially a dump for just writing useless stuff inside of it, which you don't need. So if you just want to jump instead of storing the return address, like this is JRRA, Essentially, what your compiler generates is a JALR instruction where the stored return address is just thrown away. And you just jump without ever being able to return because there's no memory to it. So what we need to do when we call several levels of functions is that we need to save the return address before it's overwritten. So this is done by the compiler automatically, and the compiler automatically inserts code at the start and end of each function to save all the registers which would be overwritten by the function, and of course to restore them later. This is called the so-called prologue code at the beginning and epilogue code at the end before we return from our function. So our code on the top in green here decrements our stack pointer by 8 bytes, so it reserves 8 bytes on the stack. We have a 64-bit RISC V here, so essentially each address, each pointer is 8 bytes in size, each register. So when we want to store our return address, we need 8 bytes on the stack. So what we do here now is we subtract 8 from the value of our stack pointer to make space on the bottom of the stack. Our stack goes downwards on RISC V, and then store the return address at the location where we want to save it, because we just made space for this. Then we have our regular implementation of our foo function here. Then we jump to our target address, which is 100, and then our link register was overwritten. So now we need to restore our link register, and that's the remaining 2 lines of code in green. So now we load our RA register again from exactly that location which we stored it to. So the SD and LD are symmetrical, so they load and store RA from the exact same address, of course. Then we fix our stack value, because when we load something from our stack pointer is not automatically increased again. This is different from, for example, x86, where you have explicit push and pop instructions which handle our stack pointer. Here we do it separately with our add immediate instruction. So we add 8 again to our stack pointer, and this is again symmetrical to our very first instruction, which was inserted in foo, where we subtracted 8. So our stack is in the original state as before the call. Our original RA value from whichever function that called our foo function is restored, and now again has the correct return address. So you see, this is quite a bit of overhead. So for our 4 instructions in black and red that actually make up our foo function, we add another 4 instructions to just save and restore the context. Obviously, this is not so bad if your function does a bit more, but there might be situations where you don't need to do this. And this is, when in recursion, called a leaf function. So a leaf function is a function which does not call any other function. So if you know, or your compiler knows it obviously, that your function you're going to write is not calling another function again, but just doing something like adding and returning, then you can omit saving and restoring the RA register, because you know it won't get overwritten, because if you don't call a function, there will be no JALR call inside of this function's machine code. And so, well, you can optimize a bit here, and this is especially often used for recursion in functional languages like Lisp. So we have function calls now. The problem is, if you look at the assembler code from the previous slide, you just give it an address. So that means if you know the address of a function inside of the memory of your computer, you can just jump everywhere. So especially you could call functions which you are not supposed to call, because there's no level of protection. So if you figure out their address, you just jump to them, and there is no mechanism to control which function can call which other function, because that would cause a lot of overhead. So essentially, this is pretty dangerous. So these library functions, well, could be called from everywhere. And essentially, we want to constrain this. We want to check if a certain function is actually permitted to be called from our program. And we want, for example, also to check if the parameters are correct, stuff like that. So we want to have something more than function calls. We want to have a controlled transition into what previously was our library functions and now slowly becomes our operating system. And to do this, we said we are going to introduce what we call privilege levels. So we have two different privilege levels, one for applications or user mode code, and one for our operating system kernel. So our operating system kernel, in its higher privilege mode, is allowed to access the hardware directly, to disable interrupts, whatever you can imagine. And our application is just allowed to execute code and call functions inside of the operating system. And now we could directly call functions from the application privilege mode inside of the kernel mode, then it could call all sorts of privilege codes without control. That's obviously not what we want. We want a controlled interaction. So we constrain our user mode code, our applications, to call the kernel at exactly one predefined location. And we don't do this using a jump or a call or JLR instruction, for example, but we do this by using a special instruction. And this instruction not only calls the kernel at a predefined location, it also automatically switches privilege modes. So on the right-hand side, you see an application calling system calls. And all the system calls end up in the same location. So if you have a print and a read character and a format disk system call, well, they all end up in the same location in the kernel at the same address and the same piece of code. So we need a way to distinguish which of the functions was actually called. So compared to a function call, which just has a name, and this name resolves to a certain pointer where this function is located in memory, we need to tell the kernel, when we enter it, which of its functions we actually want to use. So each system call, compared to a function call, has a so-called system call number. On the right-hand side, we might have a system call 1 to output a character to the screen, a system call 2 to get a character from the screen, and a system call 23 to format our hard disk. So whenever we enter our kernel using a special machine instruction eCall, we end up at the same location. So the first thing we have to do is to check this system call number that we just passed, and then the kernel checks, okay, it's system call 1, we want to print something. Perfectly fine, this process is allowed to print something. Then internally, it would still, of course, call the putchar function, which, for example, directly accesses the hardware to output a character on the screen. And you've seen this before in your bare metal Hello World, how this works in our emulation. The same with getchar, so we need to read the character from our keyboard, for example. And then finally, our application tries to format the hard disk. Now, common applications should not be allowed to format hard disks arbitrarily, obviously. So the operating system could now check, okay, that's application number 42, and it tries to call syscall 23, which is formatting a hard disk. And that's not okay, because it doesn't have privileges to do this. So instead of formatting the hard disk now, which would have happened if we would have just called the function directly instead of through a system call. So instead of formatting the hard disk, our operating system complains and either returns an error message, or depending on how you implement your OS, could just kill the process because it thinks, oh, this is a malicious process, it should never be allowed to do it, so let's better get rid of it, who knows what else it's going to do. So our kernel should be able to check parameters, it should be able to check which system call is required, and we need this controlled interaction, this controlled transition from user to system mode in order to enable this. So everything that's below our line is our operating system kernel, privilege mode. Everything above the line is then one or more applications which try to use operating system functionality. So privilege modes are available in almost all modern CPUs except for the smallest microcontrollers where like all code runs in privilege mode because it's not a lot. On x86, so Intel AMD machines, you usually have like 4 different privilege levels which are called rings. You might have seen this before in the IRBS course. RISC V has 3 privilege levels. So there's the least privilege level called the U or user mode. This is the mode where your applications and also your user mode libraries run in. Then we have a supervisor mode. this is the mode in which your operating system runs in, so the S mode. And then we have another mode, which is a machine mode. And this machine mode has completely full hardware access. So we can even constrain an operating system from accessing certain functions in the hardware, because nowadays, of course, modern CPUs should be able to run several operating systems at once using virtualization features. And so this additional machine mode enables us to do exactly this. Now ignore the hypervisor and running multiple operating systems at once, because, well, we only want to run and write one operating system now. So what we need is we need to switch between these modes, for example, from user to supervisor mode. And we've just seen we can do this explicitly. So when we explicitly want to call a function inside of the operating system, we use this eCall instruction, and before we call this eCall instruction, before we execute it, we put all the parameters for this functionality we need, so the syscall number and any parameters in registers, and then we execute eCall, and then the operating system is automatically invoked in its own privilege mode, and then can check all the parameters, and if they're right, execute the function. But it can also happen implicitly as a side effect of something happening on the hardware. So in computers we have interrupts, for example a timer interrupt which ticks maybe every 10 milliseconds and enables the operating system to do regular tasks, or enables the operating system to keep count of time, or enables the operating system to finally switch between processes which are running on your machine. But it can also happen as a side effect of executing an instruction. So for example, when you try to access a memory location but there's no memory, your hardware might generate an error signal which might lead to a failure condition inside of your CPU, and it generates a so-called trap. Or you could have an illegal instruction inside of your program. For example, if you accidentally jump inside of a bit of data like a JPEG file, and this bit pattern, because the CPU doesn't know if a bit pattern was intended to be an instruction or just a pixel on a screen or something, this bit pattern is not a legal instruction bit pattern, your CPU would complain. Or something else, like if you try to divide by 0, that would also be an error condition in most CPUs. So we can switch explicitly, so inside of our program control flow, and the switches can also happen implicitly by a side effect of something happening in the hardware. Now, obviously, the hardware, the CPU, cannot override the RA register, our return address, when it enters the kernel, because there was some valid value in there. And remember, we only have one RA register in the CPU, so there's not a separate one for our supervisor or machine mode. So that means we need a separate location to store this information where our program was originally interrupted. And in turn, returning from an operating system is not just JRRA as we've seen with regular functions, but we need an instruction that not just returns somewhere to this special location which we stored, but it also has to switch back privilege modes, for example, back to user mode after a system call, because otherwise our program would continue to run in supervisor mode and have access to all the hardware. So there's not just an eCall instruction, but when you want to return from M mode, you use the mret instruction, return from machine mode, or when you are in S mode, use the sret instruction to return from super mode to whichever mode you've been in before. So it could also happen that you have something taking you from supervisor mode from your S to machine mode, and then if you executed an mret in your machine mode code, you would just be back in the supervisor mode, executing with supervisor privileges. So we have a controlled transition from user mode inside of the kernel using this eCall instruction. It's a machine instruction which takes no direct parameters, but of course you have to prepare parameters in registers for the operating system to know what you actually want from it. It switches our processor to, in our case, machine mode. So we make life a bit simpler for ourselves. We let our operating system run in machine mode instead of supervisor mode. And so essentially, we don't use the supervisor mode in our operating system to keep things a bit more simple. So we always switch from user mode, where our application runs, to machine mode, where our kernel runs, our operating system, and back. The eCall instruction causes the CPU to store the previous processor state, so which was the previous CPU mode, were interrupts enabled, whatever. And then the important thing, we said there's one central point all these exceptions transfer to, so it jumps to a central address, which is called a trap vector, which is an address inside of the kernel. And to go back from our operating system kernel functionality to user mode, we have this controlled transition back to the previous mode. So we use M or SRED depending on which mode our operating system runs in. So MRED for our examples here. And I just explained why you cannot use a simple JRRA instruction. And this is because we need to restore the previous state, which is a simple jump to a register would just not do. Now, the question already came up, where on earth are we going to return to if it's not in RA? So RISC V has a number of special registers for exactly these use cases. And these are called CSRs, configuration and status registers. And this CSR contains, there's a special CSR which contains this so-called exception PC, separately for supervisor and machine mode. So this CSR is called MEPC for machine mode and SEPC for supervisor mode. So when an eCall instruction or another trap actually occurs, we switch, for example, to machine mode, and then the CPU stores the address at which the program was interrupted in our MEPC register, for example. And then there's this MRED instruction which reads the MEPC register, restores the privilege mode to the previous mode, and then jumps to that address which is given in the MEPC register. So this all happens automatically. So if you use MRED, then this works automatically for you. So we've already seen a bit about parameter passing for function calls. So in most CPUs, parameters which you pass to a C function are passed in CPU registers. Obviously, there's only a very limited number of CPU registers. So for early x86 machines, you couldn't do this because you only had like 4 general purpose registers available. You were running out of registers pretty easily. So x86 passes parameter on the CPU stack, at least in the 32-bit versions. On RISC V, we have 32 registers, so we can afford to use some registers to pass values. Why can't we just put them on the stack? Well, we could, but we would have to write them to the stack from registers first, then we'd have to switch to the kernel and read them back from the stack. That's quite a bit of overhead, but just putting them into the registers, well, the register values are still there after we switched to supervisor or machine mode, so it's just a bit faster and more efficient. Now, which parameters are passed in which registers, which parameters are returned in which registers, as I already mentioned, this is defined in our application binary interface. So each CPU platform, like RISC V or ARM or x86, has such a document that describes, for like example C code running on Unix, A0 is the first parameter for RISC V, A1 is the second, A2 is the third, and return values are always passed back in the A0 register. Now, the problem exactly is that each processor register is only available once. So our compiler generates code that keeps intermediate values in registers. And, well, you can call a function from very many different pieces of your code or places in your code. So that in turn means the compiler doesn't really know when it compiles a function, which other functions call it. So if our function we just compiled overrides registers and then returns, well then the original register values that the function had used before, they're overwritten. That's a problem. So registers have to be saved if you need the value after the function call. And in this ADI there's a specification, so some registers have to be saved by the caller, so the function executing this JLR function, and some other by the callee, so the function that's called as a target of the JLR instruction. Your compiler does this automatically. So in addition to inserting a code to store the RA register on the stack and retrieving it before returning, it also inserts prolog and epilog code to save all the registers either before jumping, if you need them later, so if the compiler knows these values are needed later, or for the callee saved registers in the epilog of a function and then restoring it in the prolog of a function and then restoring them in the epilog. Now an exception is different because an exception is not happening under program control directly. So when I have a function call and I compile it, of course the compiler knows that we have a function and can insert this code. But here we just have an eCall instruction and there is no C code equivalent for eCall. So we have to insert a machine instruction directly here. So the compiler has no clue what's going on there. The compiler does not know the calling context. The compiler only knows this for functions, for C functions called directly in the C code. So if the operating system then overrides some of the CPU registers, that would also be pretty bad because when we return to our user mode program then, it continues calculating with incorrect values in registers, and that's not what you want, obviously. So we need to do something about it. So we need to take a closer look at how to implement and how to call a system call. So we've already seen a function call uses a subroutine call instruction JLR RISC V, and the destination of the call where we want to jump to is given in the target address which we pass to this JLR instruction. Whereas the system call uses an eCall instruction which does not take a parameter, so all syscalls and some other stuff always jump to the same function inside of our kernel, which is our exception handler. Because we said we cannot allow user code to directly jump to arbitrary locations inside of our kernel. And we already said we need to be able to identify which function our user mode code actually wanted the kernel to execute. So we've already seen our system call numbers, and this is yet another convention, so each operating system defines which number corresponds to which functionality. So for example, in the XV6 operating system, which is a small educational operating system developed by the MIT, which runs on RISC V, you have these syscall numbers on the right. So these are just like C constants defined in the preprocessor as macros. So all of them start with sys and underline to identify, well, this is a system call number. And then you have the names of this functionality inside added to the right. So a fork system call would have the number 1, exit number 2, wait number 3, pipe number 4, and so on. So what your user mode code has to do is when it wants to call one of these functions, it has to write the number of the system call into a certain register. So for RISC V, the calling convention is that the number of a system call is contained in register A7. Then it has to write any optional parameters like a character we want to print into the registers to pass parameters. So for example, if we have a print character function, we have one parameter, the character to print, and we would put this into A0, the register holding the first, and in this case, only parameter. And if you have more, you would A1, use A1, A2, A3, up to A6. Okay. So which registers do we have to save when we call an operating system function, so a system call? So we already said the application binary interface, when we call regular functions, describes the registers to be saved by the caller of a function and by the called function. But this only works if C functions are called in a regular way, not as an exception handler. Now you could say, oh, we know there's an eCall, we could insert code, but the compiler doesn't know what an eCall does. And we also said exceptions can handle in different circumstances, like, for example, trying to divide by 0. And of course, if we just have a division instructions, just in case something can go wrong, saving all the registers before doing the division and restoring them later, you can imagine this is a huge overhead. So this also means we cannot simply use a C function as the exception handler, because that C function would just save the callee save registers, but since the compiler, in case of an exception, so an eCall instruction or a trap, has never saved the caller-saved registers, these would still be overwritten by our kernel function, and then we will continue to calculate with incorrect values after we return from our kernel. So we have an invariant here. So all of the CPU registers need to be in the same state after returning from a system call or exception as they were before. So before I called the eCall or before I accidentally divided by 0. The only register for eCalls that may have a different value is the return value register. So system calls return information on did they work, did they not work, was there an error? For example, I tried to read a file that did not exist, or I tried to write something to disk and the disk was full. So a return value, like with functions, is passed in register A0. So the kernel writes something to it. So this means we need to insert code inside of our kernel at the very start of our exception handler, of our trap handler, to save all registers to make sure that the program returns to exactly the same state it was in when the trap was executed. So how can we do this? Let's build some syscalls to do this. We've seen system calls provide functions commonly used by applications, usually functions that require direct hardware access or functions that access like shared things, like a shared memory region between applications. And in our example, we have just seen 3 system calls here. So we have a function to output a string of characters, so cstring just as a pointer to an array of characters. And if the character has a value of 0, then we know this indicates the end of a string. And then we have a similar system call which just outputs a single character which we pass to it. And then we finally have a third system call which does not get a parameter but returns the character that was typed on the keyboard. Obviously, we can have more parameters in the future. So our register calling convention says that parameters are passed in registers A0 to A6 and then the system call number in A7. So we can have a maximum of 7 parameters here. This is usually not a problem. Most system calls don't take that many parameters. If we need more, we would still put them on the stack, the additional ones, not the first 7 ones. So that would be a bit slower, but this would be a very exceptional case. So why don't we start with system call number 0? Well, we could do this, but having no valid system call when accidentally there's a 0 in register A7, that might help to catch some bugs in user mode code where some programmer forgot to set the system call number or something like that. Or when you jump to a data region which accidentally has the hexadecimal value that corresponds to the eCall instruction. So this is a bit of a safety net, not a lot, but it's pretty common to do it that way. So how can we now map a function call to seek in C code, like put a jar or something, to a system call? Now we need to write a function, which is usually a library function, which actually does all the parameter passing, so writes the values to the right CPU registers, and then executes the eCall and checks the result value. So what we can do is we can write a C function that is what we call a stop for every of these system calls we're implementing. And that is what on a regular system like Unix, your C library does for you. So if you put some name of a system call like fork inside of your C program, then your compiler does not generate code to execute an eCall with fork directly because the compiler doesn't know how system calls work. Because the compiler could also be used to generate code for a different operating system, which has different system calling conventions. So there's this stop code in the C library, which has the name fork, and then puts the parameters in the right registers, does an eCall with A7 on RISC V with the set to the number 1 in this case, our system call number from XV6. For fork, we defined different ones, and then does the eCall and hence the return value. All right. So by the way, we should mention something about RISC V. We've seen all these registers A0 and RA and something like that, and that's a bit confusing because if you've seen other RISC CPUs before, you noticed, oh, they just have a regular register set, so registers, if we have 32, are just called R0 to R31. Now this is similar on RISC V, so registers are not called R, but X for whatever reason, and we have registers X0 to X31. These names we are using, like A or RA, A something or RA, are just additional names, aliases for these register numbers, and you see the mapping on the lower right-hand side of the slide here. So register X0, which, as we already mentioned, always reads as 0 no matter what we write into it, has a symbolic alternative name of 0, obviously. Our RA register, which we used, is actually the physical register X1 in our CPU. Our stack pointer is X2, and then you see further down we have our A registers. So A, why is this called A? This is usually a shortcut for argument. So argument is just another name for parameter. So A0 by convention, and this is just a convention, should contain the first parameter, A1 the second, and so on, and A7 then our system call number. So we already said when we call our system call using an eCall, we need to restore all the state of our program, so all of the registers. And our C compiler regularly does not have access to CPU registers directly. We see in a bit how this can actually work using what we call inline assembler code. But here, if we just let our C compiler generate code directly, then we already have an epilogue and a prologue generated for us, which does not do the right thing because it does not save all registers, and it could override one of the important registers of the user mode program just by using automatically generated prologue code, because the compiler doesn't know if we write a C function that this is intended to be a system call. So here we need to add a bit of machine language of assembler code. And this is just doing the storing of our registers as we've seen with our stack pointer at the beginning of our lecture. So our function starts at something we call a label, AX colon on the top left-hand side of our code. And this is just EX for exception. So something that happens when we call a trap or call eCall. And this is just a name for a memory location. And then we reserve space on the stack. So now it's not 8 bytes, but it's a huge amount of memory, 256 bytes. And we need to store all the 32 CPU registers. So we need 32 registers times 8 bytes, which is 256. And then we store them to the offset. So we store our return address to 0 of SP, which means just address SP plus 0 added as an offset. And then 8 bytes above this, we store our next register, SP itself. Then we store GP, TP, T0, and so on, until we end up storing T6 down there. And then we call our C function, which is in the kernel, which is our exception function. So we call our exception then here. This is code, by the way, from the XV6 operating system, which does this, but this is very common code you see in almost all operating systems. So our code continues on the right-hand side of the slide. So after our function call to exception, which works like a regular function call in C then, after this returns, because we need to restore our registers again. So we do everything in the opposite order. So we load our registers from the stack again. With one exception, we are not loading A0 here, because A0 could be the return value from our exception function. So we're not overriding this here, because we know this is the only register we are allowed to override after returning from a system call. Finally, we add back 256 to our stack pointer, so our stack is in the original state as it was when we entered our X function. And finally, we execute mret. So we return from machine mode to the value stored in the MEPC, in this exception PC register that was automatically written when eCall or a trap has occurred. So this is just like boilerplate code to make sure that all of our state is in the original state again, obviously, when we return from a trap. And so all the magic happens inside of this exception function, which we call here in blue on the lower left-hand side. So this is just a reminder how to determine where to return to. So some architectures actually store this information on the stack of the interrupted program, and this makes it more difficult to retrieve it because then you have to figure out what was the interrupted program stack pointer and then the read memory to figure it out. RISC V, as we've seen, has the special CSRs, MEPC, SEPC, and we can automatically jump back, as we've seen before, to the address of the eCall or the address of an instruction like the division by 0, which causes the fault. Now, compared to a regular JALR, which actually jumps back to the following instruction after the JLR. Here we really have the address of the instruction causing the transition to kernel mode, so causing this trap. So it would be the address of the eCall itself, for example. Now we do this because we might want to re-execute an instruction that has caused a trap. One example would be an instruction that accesses a virtual memory address. We'll talk in detail about virtual memory later in the course. And this address was not in memory. So there was a virtual address, but no physical memory backing this. So obviously we can't read a value from a non-existing memory address, but we want to be able to continue the program by just maybe swapping in that page of memory from disk. So what happens is a load instruction would fail because it would access a virtual address for which no physical memory is currently present. This would cause a trap to the operating system. The OS would then load required data into physical memory at a virtual memory entry. And then, of course, this load has to be retried to finally load the correct value. So for exceptions, we jump back to the instruction which caused the exception. So for eCall, we have to be careful here, because if we just jump back to the address in our MEPC register using MRED, then we would execute the eCall all over again, and we would just execute system call after system call, but no longer be able to continue with our program. So we need to do something special in the case of a system call, of an eCall handling in our trap handler, in order to make sure that we continue after the eCall. So it behaves like a function call, but all the other traps behave like they're intended to, so retry the failed instruction. So how do we determine which mode to return to? Now the CPU does this for us. So MEPC and SEPC, these two CSRs, only store the previous address, but not the previous mode. So an exception that switches to M mode could come from either supervisor or user mode. So there's another configuration and status register called M status, and this provides a very small stack, well, essentially just a couple of bits, with the privilege modes. So each privilege mode hex that can respond to interrupts has such a two-level stack of interrupt enable and privilege modes, and these bits then are automatically handled by the CPU when an eCall or a trap happens and when you return from this. So this is just additional information, and in most cases you don't have to care about this because the CPU handles this for you. If you think this is complicated, it is, but don't worry. You need to set up a bit of code to do this, but we'll provide the correct setup code. If you're interested, try to figure out what it does from the RISC V documentation. But if it's difficult to understand, that's perfectly fine, and we can discuss this later. So a quick detour here. So we said we have a bit of assembler code to store and restore registers when we call a trap. Now, if we only need a single instruction like an eCall in between C code, it's very inconvenient to call an assembler function for this because you have another source file which you have to link and so on. So sometimes we will just want to insert a single machine instruction right in the middle of some piece of C code. And inline assembler is a very convenient way to directly do this. Now, inline assembler is an extension, so this is not in the C standard. This is an extension introduced by GCC and also Clang. And this has some consequences. First, of course, your code becomes non-portable. If you insert a RISC V machine instruction in the middle of your C code, that obviously can't be run on an x86 machine, for example, or an ARM. So assembler instructions are always specific to a given architecture. The alternative, as I mentioned, is called an explicit assembler function for every required assembler instruction, which is a bit of overhead. So we need to interface between data in C, which is kept in variables, and data the assembler uses, which is kept in registers. So we have to tell the compiler when we use inline assembler, not just the instruction, but also which variable values should appear in which registers. And after the assembler instruction has finished executing, which of the register values should then be copied back to which variables. And then, if our assembler instruction uses some additional registers in between, we tell our compiler these are what we call clobbered. So our assembler instruction, which the compiler doesn't know anything about, so it just copies it almost verbatim into the generated machine code. So what happens is if this instruction would change additional registers except for the output and input operands, then we need to give them in a list because the compiler doesn't know about these, and then the compiler tries to avoid these using these registers or store them again before calling the inline assembler code. So here's one example. So the operand specifiers are format string, which works a bit similar to printf strings. So here on the lower hand, on the lower side of the page or of the slide, we have a bit of a C code which uses inline assembler. So we have like three variables here: 64-bit integer, unsigned integers, x equals 23, y equals 43, and a variable z, which should contain a return value. And now, of course, we could write z equals x plus y, and we want to do this in assembler. So we we insert this inline assembler function ASM, and in the brackets we say, okay, this should insert a machine instruction add to two values, and then we've seen the first value of add, the first parameter is the result register, and the second and third are the two parameters. So we say, just in order, so that %0 is equivalent to the first R we give after the colon here. So equals R means it receives a return value which should be stored in variable z. And after the second colon, we read two register values x and y, and these end up in %1 and %2, so as a second and third parameter of our add call. Essentially, no matter which registers our variables are currently stored in, it generates the correct assembler code. And we don't have to care about the compiler does this for us. So our clobber list here after the third colon is empty because we only use these registers that our add instruction uses. Now, sometimes compilers are a bit too eager and they want to optimize code away and even assembler code. So you can also use volatile as a keyword after the assembler ASM statement, so as in volatile, to tell the compiler, keep your fingers away from optimizing that code. So sometimes you want to write like a delay loop which uses NOPs, so no operations in the CPU, which, well, don't do anything obviously except wasting time. And of course, a compiler is keen to optimize no operation instructions away, and using as a volatile, you tell the compiler, okay, keep your dirty fingers off my code, right? I want this exactly as it's written here. Don't try to optimize it. And that's very useful. So we have CSRs. How can we access them? Obviously, our C compiler also doesn't know about CSRs. So they're not mapped into memory. And of course, they're not mapped to any variable somewhere. So we need, again, assembler instructions to access these. So there's two assembler instructions, CSR R, so to read a CSR, so it copies a value in this given number, CSR number, which also have names, into a CPU register, and there's the corresponding instruction CSR W, which writes a CSR. So it copies a value which results in a CPU register into the CSR. So per execution mode, so M mode, S mode, U mode, we have up to 4096 CSRs defined, and since nobody can remember the numbers, we have names like MEPC, which we just seen is the EPC value, the exception PC value for M mode. There's another one called mHeart ID, which contains the processor number we're executing on. So if you want to know the number of the processor we're currently executing on, we can read mHeart ID into register A0 using the CSRR instruction as shown here in blue. Now obviously this might be privileged again. So a register M hard ID is only accessible if your code executes in M mode, for example. And we can use this from C via inline assembler. So we can just return the value instead of giving a 0 directly. The second line in blue replaces this by a %0, so placeholder, and we say we want this value to be returned in the variable x. Now, this is one of the stupid parts of RISC V implementation, because the number of the CSR we want is directly encoded in the instruction instead of passed as a second parameter. So it cannot be passed as a register value, so we cannot write one generic CSRR or CSRW C-wrapper function. We have to write or generate a function for each of the CSRs we need. This is a bit strange, but that's the way it is in RISC V, unfortunately. So when our CPU starts or CPU resets, it always starts in M mode, because of course everything has to be configured first. You have to have all privileges. So how can we actually start our first application, our first instruction in user mode? Well, we've seen to return to user mode, we need the mret instruction. But we've also seen that usually the value the mret uses in MEPC, this is generated by the CPU when, or stored in MEPC by the CPU when an ERET instruction is executed or a trap is called. But after reset, nothing like that happens. So where on earth shall we continue in user mode? Well, that's a classical chicken and egg problem, obviously. So we need to do the first switch to user mode like manually. So we need to tell the CPU where to return to, and we can do this by writing a value into this MEPC register and also into mStatus to set the previous mode's bits to U and enable interrupts, so it knows, the CPU knows that it has to return to U mode. So we can use this CSRW instruction to write values into MEPC and into mStatus. So when we return from the kernel into user mode for the very first time, which means we start the very first user program, then we can tell the CPU where to jump to. So this is a bit of setup code, also taken from the XV6 OS. So we start reading our CPU status register, and we say we want our previous mode, which never existed, so we fake our previous mode to be returned to be the user mode. So that's the mStatus MPP U up there. We write it to mStatus using the function wmStatus, which we'll take a look at later. And then in the next line, we enable the interrupts by writing the mStatus register again. We could do this in one step. We're just doing this in separate steps to make it a bit more clearer. And we write another register to enable interrupts on the CPU, because otherwise we would never probably return from user mode except when an eCall is executed. Now, we've seen our kernel jumps to a certain address in the kernel, or CPU jumps to a certain address inside of the kernel when eCall is executed or a trap is happening, but we never defined so far where actually to jump to. So this specific one single location inside of the kernel where to jump to, this is not fixed. We can also configure it, and that's yet another CPU CSR, which is called mtvec, so the trap vector. And so what we do here in the w_mtvec instruction is we write this mtvec CSR with, well, something which is UN64 of x. What the heck is this? Now, x was the name of our assembler code, which saved all the registers and later restored it. So this is a function pointer, so it's just the address of this x function. So the CPU knows when a trap or an eCall occurred, it changes the PC to the address of the x function, so to the first instruction of the x assembler function, switches privilege modes, and continues from there. The UN64 in brackets is just to convert it, because x is a function pointer, so the compiler doesn't complain because this is just a regular 64-bit register. We just do a typecast to an unsigned 64-bit int. The next instruction means we disable paging, so we have virtual memory in the CPU and we don't want to use it, so we write a 0 into the register. So that means the logical addresses our program generates are identical to physical addresses. And then we have to do something else, which RISC V relatively recently introduced. So in addition to virtual memory, we have something called physical memory protection. So the WPMP instructions, we'll discuss them in detail in a bit. These just switch off physical memory protection. So we have access to all memory, so we don't have problems with this. And now finally, the last two instructions, WMEPC and the as in volatile, finally tell our CPU where to jump to. Where do we want to jump to? We want to jump to main. So to the start of a C function, for example. So we write our M mode exception program counter with, again, typecast with the address of the function main, so the address of the first instruction, and then we insert an inline assembler function which just calls mret. So this then takes the address of main, returns to the mode we've configured before, and then we continue running in main with lowered privileges. So that would be setup code for a simple OS. This requires a deep understanding of what's going on in the CPU, so please read up in the RISC V databooks if you don't understand what's going on. And, well, if there's problems, of course, just feel free to ask. A quick detour, which you might have already seen, how can we set and reset single bits in an integer? We've seen like there's defines for M status, MPP, M mode, so the privilege mode for M, S, and U. And these have like something which you see on top here, like 3L left shift 11. What the heck does this mean? Now, left shift 11 means we shift a bit or a value 11 bits to the left, of course. And this could be an arbitrary value as big as your registers. So if we have 1L just means a long value. Yeah, so essentially a 64-bit value for our RISC V. If we shift this 11 bits to the left, this means our 1 here is just shifted to, well, bit position 11 instead of 0. And this is a very convenient notation simply to avoid putting like arbitrary hexadecimal values which represent the same bit values there. And now you can add a bit to a value by ORing it. So on the code on the lower left-hand side, you can see X and equals, X or equals. So OR equals sets a certain bit, and equals here is used with the tilde. So this is a binary negation of a mask. So with and you can mask out certain bits. So we mask out all the bits we want to set, and then we override them here. So this is something you might have seen before, but I think it's worth repeating it here. So physical memory protection, as I said, is an additional mode in addition to virtual memory to help with isolating programs against each other and against the kernel. We have details on paging later in the course. If you want to know more details on paging and segmentation right now, you can check my NTNU operating systems course, which is on my homepage linked or on YouTube. We can combine paging and PMP, but PMP is always active in S and U mode. So whenever we switch from M mode to S or U mode, we need to enable access to physical memory for the code running in S and U mode. And that's what these two WPMP instructions in our setup code did. By default, all memory access is prohibited. So that would mean if we would not configure the PMP before jumping to S or U mode, then the CPU would try to fetch the first U mode instruction, for example, from memory, but it's not permitted, so it would crash immediately, and then you'd have an endless trap, which is what you not want. So this was enforced in QEMU version 7, we're now at QEMU 8, and it's also enforced in real hardware. But if you look at example code on the net, for example, there's a Rust example for writing RISC V operating system by a guy called Stefan Marks. This code doesn't do this, so this code wouldn't work with real RISC V hardware and doesn't work with the current QEMU. So PMP is always active, and we just have to disable the protection using this WPMP stuff. Paging has to be explicitly enabled, and we've seen this write to the SATP CSR, and if we write a 0 to it, it's disabled. If we write something else to it, then it sets the root address of our page table. So if you know about virtual memory, that's fine. If not, you'll learn about this later in the course. It's not that relevant right now. PMP and paging is always off in M mode. Paging in addition is off by default and has to be enabled explicitly. So here's just a more detailed description of the physical memory protection. So these in general define segments. So a start address plus a length, and you can set certain permissions. So permissions are read, write, execute. So are you allowed to read the code, read data in this address range in this segment? Are you allowed to write data in this segment? And this execute bit means is the CPU allowed to fetch instructions from that segment here? And the first so you have up to 32 or 64 even on depending on the RISC V implementation. You have up to 64 different regions. Again in CSRs, the PMP CSRs, and each of these registers or a set of registers defines the starting address, the length of the segment, and the mode that's allowed. So RWX for read, write, execute. And the first segment starting from 0 to 63, the first segment that contains information about a given address we're trying to access is the one that's used. So if you have something later, that will be usually be ignored. So currently, if you look at our startup code again, we just set the thing to actually permit all memory access. We can be a bit more restrictive later on. And here's just, again, there's different modes. I'm not going into details here. If you're interested, read them up. Currently, we don't concern ourselves with this too much. So what's finally left to do is write our C handler code for exception handling. So we've seen from our EX assembler function, we called a C function. Well, we didn't know it was a C function back then, but this one is, which is called exception. This doesn't get a parameter, so it has to fetch them from somewhere. So from the registers somewhere. Then it has to decode the syscall number. And now we've seen our problem. And this problem was when we returned from an eCall using mret or sret, then we said that the address of the eCall is what's in MEPC or SEPC. And that would mean we would just jump back right and re-execute the eCall all over again. This would mean we have an endless jump from user mode to kernel mode and directly back to the eCall instruction and so on. That's not what we want. We want to make sure if the instruction was an eCall that we actually return to the instruction after the eCall, like with a function call with a JLR. And we have to do this by hand. So if you look at the code in red here, we read our MEPC register here into a variable PC, which is a 64-bit uint. And then we write PC plus 4 back. So eCall as an instruction is always 4 bytes in length. So we know that the instruction that comes after the eCall in the user code memory is always at the instruction of the eCall instruction plus 4. So that's a trick we can use. If it was an eCall and not another prep, we have to add 4 to this MEPC value in order to return to the instruction after the eCall. So this is critical. Without it, we would just be stuck in an endless loop when we call an eCall. So what we can do is we can try to restructure our OS. We can try to separate kernel and user code, add an exception handler for all of our system calls, and we can have some files, which we'll discuss later, because you're currently still working on the first exercise. Essentially, these will be parts which we'll give you for the next exercise, where you will start to write a bit of piece of code for your operating system in the next exercise. So I'm not going into details here, but we just mentioned that here, that we try to structure our code in useful ways, so to separate functions like startup code, like exception handler assembler code, like setup code, like kernel code, and of course our user mode application into separate source files, so to have a more clean structure of our code. So if we could do this, we haven't done this yet, we would have built a 1960 style OS, or maybe a very primitive version of MS-DOS. So if you had done this like more than 40 years ago, you would be a billionaire now. Well, Bill Gates actually bought MS-DOS from a programmer and just paid this programmer $50,000 for it. And Bill Gates became a billionaire, not that poor programmer. It's single tasking. It would only be polling. We didn't discuss interrupts yet. DOS used them, so it's not quite DOS what we're writing. We've seen that system calls are defined interfaces from user to kernel mode, and we can force user mode instructions where if they want to use kernel functions to use these defined calls only because they have no other way to execute kernel functionality. And then in turn the kernel is able to check all parameters for validity, check for permissions if we're allowed to format our hard disk and so on. In our next lecture, we'll discuss how to protect an operating system, how to use PMP for basic protection from so how to protect the kernel from user mode accesses, to enable separate address spaces for OS code and user mode code, and also how we can compile our executables separately, because executables currently are just linked to our kernel, but we'll discuss this in the next exercise session, so next week after I return from Rome. So that's all for today. Thanks for watching and listening. So here's some additional references. So the RISC V instruction set manuals give you all the details about CSRs and instructions and so on. There's some additional stuff by Daniel Mangum on RISC V. There's this OS course in Rust by Stefan Martz I mentioned, which needs some updates. There's the description of XV6, which describes a lot of the details, and then a lot of the stuff in GNU compilers links. And there's also the operating systems lecture 9 on memory management. This is no longer available, unfortunately, on this URL. Sorry, I forgot to update this. You can find this on multicourse.org, which is my private web server, but I'm going to show you this later. So thanks for listening again, and until next time, bye.